Buried beneath city streets and carved into mountainsides, machines exist that slice stone with surgical precision, move molten slag hotter than lava, and pulverize forests and waste in minutes. Every inch of modern infrastructure depends on these engineered giants. But behind their power lies a simple question: how do you control a force that could destroy everything it builds? Subscribe for more stories that reveal the hidden decisions shaping the world's most extreme machines, and discover what happens when absolute precision meets unstoppable force. A trencher's chain meets Earth with a purpose that borders on surgical. Each steel tooth is set at a precise angle, pitch, and spacing calculated to slice through compacted soil and fractured rock, not just with brute force, but with discipline. The chain's articulation allows it to follow subtle curves in a planned utility path, holding a trench wall as crisp as a blueprint line. Engineers spend months refining the geometry. Too steep an attack and the teeth stall or shatter. Too shallow and the chain polishes the dirt instead of cutting. Spoil control is just as critical. As the chain rotates, self-clearing rotors keep debris moving up and away, preventing jams that could halt progress for hours. The result is a trench with walls that won't collapse onto new water mains or fiber conduits. In the field, design engineers walk the cut, checking for wall breakage and measuring the trench's tolerance against the original plan. One engineer, boots caked in clay, points out how a half-degree change in tooth angle last season meant fewer stoppages and a cleaner finish, even through pockets of dense gravel. Every pass of the chain is a negotiation between steel and earth, precision that makes it possible to lay the invisible infrastructure modern life depends on without tearing up more ground than necessary. At the heart of a steel mill, slag transporters crawl between furnaces and pits, each carrying a vessel filled with molten byproduct glowing at over 1,400 degrees Celsius. The shell of every pot is a fortress of cast steel, but it is the skull, a layer of solidified slag inside, that shields the metal from the full fury of the heat. If that skull thins or cracks, the risk is not just downtime. A breach can send a river of molten slag across the floor, threatening equipment and lives. To keep this from happening, operators rely on refractory linings tailored to the specific chemistry of each batch. Magnesia is used for basic steel slags, alumina for others. Sensors and thermal cameras scan for hotspots that warn of danger before disaster strikes. Out in the yard, the story shifts from searing heat to relentless abrasion. Forestry mulchers, fitted with carbide-tipped rotors, grind entire trees into chips in seconds. These rotors spin at thousands of revolutions per minute, flinging debris against reinforced cabs designed to withstand flying wood and stone. The carbide teeth resist wear that would shred ordinary steel, keeping machines in the field longer and operators protected from the chaos outside. In composting operations, the focus is on life rather than destruction. Massive turners aerate mountains of organic waste, their drums lined with wear-resistant alloys to survive constant exposure to moisture and microbes. By churning and oxygenating the pile, these machines accelerate decomposition, turning waste into stable, usable compost in weeks instead of months. Whether holding back molten slag or enduring the grind of wood and waste, these machines are built for environments that would destroy anything less prepared. Each design choice, skull thickness, refractory blend, and carbide edge stands between controlled industry and catastrophic failure. In open pit mines, the scale of excavation defies ordinary experience. Hydraulic mining excavators like the XMG XE7000 weigh over 670 tons and rely on twin diesel engines to drive immense pumps, forcing oil through networks of reinforced hoses. Each hydraulic cylinder delivers enough pressure to lift a city bus with a single push, yet the operator controls the boom and bucket with millimeter precision. Power flows from engine to pump to actuator, translating raw combustion into measured force that can shear through dense overburden or load a 400-ton truck in just a few passes. Maintenance crews, boots deep in dust, check for leaks and monitor pressure gauges. Any drop hints at a worn seal or clogged filter that could bring operations to a halt. Nearby, electric rope shovels like the P and H 4100 XPC draw their power not from onboard fuel, but directly from the grid. High voltage cables snake across the pit floor, feeding continuous current to motors that hoist and swing a 100-ton bucket. Unlike hydraulics, these machines never idle. They're digging rhythms set by the pulse of the substation. When a cable frays or a power surge hits, the entire cycle pauses until a field technician splices copper and resets breakers. Two philosophies, hydraulic muscle versus grid-fed endurance, work side by side, each engineered for relentless, decades-long duty. A maintenance manager, clipboard in hand, inspects the boom pins and cable reels, knowing that every hour of uptime is measured in thousands of tons moved. A haul truck idles at the edge of a mining bench, its cab rising above pickup trucks parked nearby. The Caterpillar 797F, for example, weighs over 360 tons empty and can carry 400 tons of ore in a single load. Instead of a traditional transmission, a diesel engine spins a generator, sending electricity to wheel motors on each axle. This setup delivers instant torque, enough to climb a 10% grade with a full payload, even as the tires, each taller than a grown man, flex under the strain. The absence of gears means smoother starts and fewer breakdowns, a necessity when a single truck's downtime can stall an entire operation. Alongside these giants, low ground pressure carriers glide over soft terrain. Wide pads distribute weight, keeping ground pressure below that of a human footprint. This matters in areas where even a small rut could trigger erosion or damage fragile soil layers. A fleet manager, clipboard in hand, checks the tire pressure and pad wear, explaining that every adjustment in pad width or inflation is a calculation. Too much pressure, and the roadbed fails. Too little, and efficiency drops. Every haul, every turn is a balancing act between power and preservation, moving mountains while leaving as little trace as possible. A bulldozer's blade, once guided only by the operator's eye and a stake in the dirt, now follows digital commands with sub-inch accuracy, with precision that was unimaginable a generation ago. Global navigation satellite system receivers, inertial sensors, and blade angle encoders work together to hold a grade line traced in the air. No string, no guesswork. The operator sits behind glass, watching a live map as the machine's control system adjusts hydraulic flow to keep the blade within a centimeter of the design surface. Every pass means less rework, less wasted material, and a finish that surveyors can verify with a single scan. In modern agriculture, tractors equipped with real-time kinematic global navigation satellite systems steer themselves along parallel lines, planting and fertilizing with precision that once belonged only to laboratories. The result is straight rows, uniform yields, and efficient use of land and chemicals, increasing efficiency. In factories, robotic manipulators grip and rotate steel beams, calibrating their end effectors to within a fraction of a degree. Sensor fusion, combining laser, camera, and encoder data, lets these arms position components for welding or assembly with repeatable accuracy. Across fields and shop floors, brute force answers to digital control, turning heavy machines into instruments of measured intent. Rotating drums carve through asphalt and concrete, stripping away layers in measured passes. Each revolution is a study in controlled force. Tungsten carbide picks bite into pavement, while internal water jets keep dust and heat in check. Technicians monitor drum wear and tooth spacing, swapping segments before vibration can ripple through the chassis and slow the entire fleet. On the shoulder, a compost turner's drum churns windrows, mixing air and moisture into decaying plant matter with the same relentless rhythm. These machines don't just build, they sustain, keeping roads smooth and soil healthy. Maintenance here is not an afterthought. It is the pulse that keeps infrastructure alive, invisible but essential to every project that follows. A bucket wheel excavator stretches across the horizon, its rotating wheels studded with steel buckets, each one scooping earth by the ton. Machines like the Bagger 293, weighing over 14,000 tons and reaching the height of a skyscraper, can move more material in a day than most construction sites handle in a year. The secret lies in their continuous operation. As the wheel turns, buckets lift soil and rock onto a network of conveyors, which carry the load away without pause. This relentless cycle reshapes landscapes, carving out coal fields and lignite mines on a scale visible from space. Yet the story does not end with extraction. On the edge of a retired plant, demolition shears, massive hydraulic jaws, bite through steel beams, slicing structures into manageable pieces. Salvage crews sort and recover metal, sending it back into the supply chain. The same engineering that powers creation now enables careful deconstruction, closing the loop between what is built and what is reclaimed. Right now, these machines quietly shape the world beneath our feet, moving more earth each year than all natural rivers combined. As demands on infrastructure and resources accelerate, their role only grows. The scale of our civilization is measured in steel, hydraulics, and ingenuity. Our future still runs on giants,